Hello everyone, this is your last lecture on VLSI Design Laboratory where we'll be learning about implementing state diagrams with the help of Verilog. Now, I won't be discussing in detail about what state diagrams are, the Mealy diagram or Moore diagram, or how uh, we can draw the state diagrams, or what finite state machine is, because everything of that sort has been discussed in theory. What I'll be doing is I'll be designing the finite state machines in Verilog. That is, we have these state diagrams already drawn. So before you go on to watch this video, you should at first watch the video where I explain finite state machines and state diagrams in theory. So after watching that, come back here and watch the video, and I think everything else will be clear. So the first example is this. Here we now, in this example, we design a Moore machine. The example says that we have to design a circuit that performs the following specifications, that has the following specifications. It has one input W and one output Z. One thing is to be said that since it's a finite state machine, it is given that you have a clock and a reset. So those things are not mentioned. Other than those, you have one input W and one output Z. All the changes in the circuit occur on the positive edge of clock cycle. That is important. The output Z is equal to 1 during two immediately preceding clock cycles. We have discussed it in the earlier video that two immediately preceding clock cycle would indicate it's a Moore, and input if input W was 1 in two immediately clock cycles, the output Z was 1 in the next clock cycle, otherwise output Z is 0. So we have to design it. The first stage of designing a finite state machine is to draw the state diagram. So we have already drawn the state diagram in the earlier videos, and we'll just be using it using this state diagram, and we'll be transferring this state diagram into our Verilog code. Now, as we start the Verilog code, the first thing that we need to do is open a new project. We are going through all the usual stuff. We have to define the place where we want to save everything. Okay, then we have this all 20. Sorry. So what we first do is we first specify the folder where we want to save it. Then we name the file. For example, at first we want to do uh, we name it FSO1. This is our first experiment on finite state machines. Next, Flex 10K, Verilog HDL in all these cases. Finish. So now we have our projects open. Now we click here, new, and from here we open a new Verilog HDL file. So before I go on to write the code, there are certain steps that I would be needing to follow. The first step is I have to define the input and output. So there are 4 steps. We have to define the input and output, define the present states, define all the states, and we have to choose whether it's Mealy or Moore. So at first what we need to do is we need to define the input output. So what we do is module FSM1. We know our inputs are W, clock, reset, and output is Z. Then we define input as W, clock. It is to be noted that W clock and reset all are single bits. And output reg Z. Since it's a sequential circuit, so we have to define Z as a register. Now what we need to do is first step is complete. That is, we have already defined input and output. Next, we have to define present state. What does that mean? That means that we have to we have to let the code know where we are at this moment, whether we are in state 0, state 1, or state 2. So the value of the present state will vary. For example, if we are in state 0 and we get w is equal to 1 in the next clock cycle, we move to state 1. So the value of present state will be varying. So the way of using variables in uh, quarters is using the function reg ps. Let us define present state as ps. Now, before we move on, we have to notice one thing, that is the number of states. Here, the number of states is 3. There are 3 states. Now, in order to define 3 states, that is, in order to define 3 in binary, we need 2 binary digits. That is, 3 is equal to 1, 1. So we'll be making 2 binary digits. So present states, since it can hold the value of state 1, state 0, state 1, or state 2, what we need to do is we need to make it a 2-bit number. Similarly, next thing, the first thing is we have defined the present state. Now we have to define all the states. Now the difference between present state is and all the states is that present state can move from S0, S1, S2, whatever. But the states S0 is fixed. That is when S0, when you're in S0, W is equal to 1 would make you perform one function, W is equal to 0 will make you perform another function, and that will be true for all time to come. So the state itself is fixed, but the present state, which state I am in, is variable. So the way of so states are since states are fixed or constants, the way of writing those down is parameter. Sorry, parameter. After parameter, we have again 1 colon 0 because we have 3 states. If we had 5 states, 5 is equal to 1, 0, 1, then we would have to put 2 colon 0. So parameter 1 colon 0, we put S0, our 0th state is equal to 0. S1, our first state is equal to 1. S2, our second state is equal to 2. So now, as usual, always at the rate pause edge. Since it has been said that it works on positive edge of clock, so always at the positive edge of clock, if RST is equal to, if reset is equal to 1, then what we need to do is, if reset is equal to 1, present state is present state uh, is equal to S0. Whenever we can see, whenever we put reset, we go back to the S0 state. So when reset is equal to 1, present state becomes equal to S0. Else, when reset is not equal to 1, there will be multiple comments inside, multiple things inside else. So we use begin and end. So if reset is not equal to 1, then what happens is, if we look at the diagram again, if reset is not equal to 1, then if present state is S0, then W is equal to 1 will make the present state as S1, and W is equal to 0 will keep the present state in S0. That is, again, if present state is S1, then what happens? W is equal to 1 will take it to S2, W is equal to 0 will take it to 0. So in the else option, everything will depend on what the present state is. So we can write it like this: case present state, sorry, case case present state. Then if case is S0, then what happens? If W is equal to 1, sorry, equal to 1, let us see the diagram more clearly. If W is equal to 1, present state becomes S1. Present state S1. Else, present state becomes is 0. If W is equal to 0, present state is 0. If W is equal to 1, present state is 1. Second case is present state can be S1. If W is equal to 1, present state becomes, we can say, S2. Else, present state becomes, if from S1, if W is equal to 0, present state becomes S0. Similarly, for S2, if W equal to 1, there's a mistake over here. For S2, if W is equal to 1, what happens is present state remains S2. So PS S2. Else, if W is equal to 0, present state becomes S0. PS S0. So what we have done is, then we have to put end case. What we have done is we have designed this state diagram. We have designed this state diagram, uh, and our code is almost over. Only there is one thing left. The thing that's left is uh, we still haven't defined the output. That is output. We have never mentioned what the output is. Now what happens is when present state is S2, the output would become 1 in, for example, here we have moved. So output will become 1 in next clock cycle. So now let us see how this code will work. So excuse me for a bit. Okay. So let us see how this code will work. Now let us suppose that the first input that we get is 1. At first we get reset. At first reset is exerted. If reset is exerted, then what happens? Our present state becomes S0. Our present state is S0. I'm going it step by step. At the next clock age cycle, reset is not excited. Let us suppose that W is equal to 1. If present state here is S0, if W is equal to 1, present state will become S1. So PS will become S1. This thing is happening at the next clock cycle. This arrow indicates clock cycle. Here we haven't put the 0 because it's in the same clock cycle. Okay. So present state becomes state 1. Again, then what will happen is present state becomes state 1. It won't go into other cases. It would again start from the beginning. It will come here and it will check what the present state is. Now present state is state 1. That is, in the next clock cycle, it will see that present state becomes state 1. Now again, if W is equal to 1, then what it will do, it will make the present state as S2. So at the next clock cycle, if W is equal to 1, it would make the present state is equal to S2. Now, had it been a Mealy machine, what we would have had to do, we would have had to do such a thing such that as soon as the present state becomes S2, Z is equal to 1. This is the condition for Mealy machine. But this is a Moore machine. So in Moore machine, we have to exert Z is equal to 1 in the next step. So how can we do that? The way to do that is, so once it gets to state S2, it comes to the end of the code, and again it starts from the beginning and sees the present state. Now the present state is what? The present state is S2. So if the present state is S2, what it should do? It should make the it should check this whatever is there in present state, and it would make Z is equal to 0. So if present state is S2, whatever W be, doesn't matter. What would it do? It would next make Z is equal to 1. So what we can do is, after the else, we can do is Z present state equal S2. Okay, what does this signify? If PS equal S2, this command gives the output of 0 when present state is not S2, and the output of 1 when present state is S2. That is, if present state is equal to S2, sorry, double equal, present state is equal to S2, it will give the output of 1. If present state is not equal to S2, it will give the output of 0. So when we started, a present state is S0 because reset has been exerted and it will not go into the else. In the next cycle, when present state is S0, so Z is equal to 0 since present state is not equal to S2. So it will go into the case. Sorry, this line has to be put after begin because it's within the else. Okay. So the next stage here, present state is S0. Then if W is uh, Z will be 0 because present state is not equal to S2. Then it will check the value of present state. It will find that present state is S0. Then it will check the value of W. If W is equal to 1, then it will make present state is equal to 1 in the same clock cycle. So here the value of present state would be S1 and it will move to the end of the code and it will come back again. After coming back again, it will compare the value of present state with S2 and it will find that present state is not S2 at this moment. So Z will remain 0. Then it will check what the value of present state is and it will find it's S1. From S1, it will check the value of W. If W is equal to 1, present state becomes S2. So at this clock cycle, the present state will become S2. The present state will become S2, but what will happen is it will go to the end of the code. That is, since it never reaches this line after S2, so in this clock cycle too, the output will not be equal to 0. So it will reach the end of the line. And after reaching the end of the code, it will start again. In the next clock cycle, it will see that present state is equal to S2 and it will make Z is equal to 1. So the logic is very simple. Uh, the output, whenever the present state becomes S2, the output will be 1 in the next clock cycle. So we have to devise our our Moore machine. So one thing is required. We haven't put n module at the end. So this is our code. We save this code as FSM1. Okay, we're saving this code and let's compile and see if there is anything wrong with the code. Okay, there are errors. Uh, say error. Okay, here we have forgotten to put equal sign. Okay, there is no more errors. So what we can do is, since the code has no error, we can open a new vector waveform file. Choose vector waveform file. We insert node or bus, everything like we have done in previous experiments. Okay. Now we have clock reset. From clock, we just put any random clock in this. Reset, during the first cycle, we put reset. We force it high. Why the first cycle? So that the initial state becomes S0. That's why in the first cycle, we are putting clock is reset is as high. Now, before we go on to define W, in our problem statement, there is a table given of input output. So if we provide the input like this, we'll get output like this. Excuse me for a bit as I clear the narrations and it looks really. So if we put this as input, we get the bottom line as output. So how does it do? At first clock cycle, W will be 0. So we can minimize it by pressing Control and scrolling down. So after reset, the first clock cycle is this, output input is 0. Next we get 1 0 1. This cycle we force the input high. Next 0, then sorry, then in two of them we force it high. Then we have 0 1 1 1 0. Then what we do? We have a 0 here, then 1 1 1. Okay. So this is our input. 0 1 0 1 1 0 1 1 1 0. So 0 1 0 1 1 0 1 1 1 0. One thing is to be noted that we have started the pattern after the reset has been taken off. That is after the reset is turned to 0. That is very important. So this is the vector waveform file is ready. We can save it. After saving it, like we always do, uh, we go to processing. Sorry, we go to assignment settings, simulator settings. We turn it functional. Processing, generate functional simulation netlist. Successful. Then we run. Okay. Now okay. Now, if we look closely, maybe we zoom a little more. Okay. So, if we look closely, maybe I should do this. Now, observe one thing. In this clock cycle, let's change the color for easier understanding. In this clock cycle, what happens is our W is 0, that is this 0, and our Z is also 0. In the next clock edge, our W is 1, Z is 0. In the next positive clock edge, W0, Z0. It's okay. In the next positive clock edge, W1, Z0. In the next positive clock edge, again W1, Z0. In the next positive clock edge, W0, Z1. Similarly, W1, Z0, W1, Z0, W1, Z1, W0, Z1. So what we can see is, we can clearly see that this table has been filled out by this timing diagram. So our output is similar to what we would expect from our Moore machine. So the code is correct. Now what we need to do is, now we want to convert it into a Mealy machine. We have already learned how we can code for Moore machine. Now we have to convert it into a Mealy machine. One thing is to be noted, as I had said in the theory class as well, the state diagram of Mealy machine and Moore machine can be the same. That is, in here I have put a different state diagram for Mealy machine, but as I've said, I can keep it same, it doesn't matter. So since I have already designed it using Moore machine, I can easily if I keep the state diagram, these lines will be same. So I do not have to make a lot of modifications. Only modifications that I need to make is, in case of Moore machine, Mealy machine, if you remember correctly, as soon as the present state becomes S2, Z becomes 1. So if we remove this from here, and if we change the output from reg, and if we do this, outside always, if we assign Z is equal to PS is equal to S2, then what will happen? As soon as the present state becomes S2, the highest priority is belongs to a sign. That is, what happens inside doesn't matter. As soon as it finds a sign, as soon as the right hand side of a sign changes, the value of Z changes. So as soon as present state becomes S2, Z will become 1, and it will not depend on the output of this particular code. That is, it will not depend on the next clock cycle. It will not depend on clock cycles. It will just be 1 as soon as present state is equal to S2. So let us compile it and see if our claim is correct. So we are saving it and compiling it. Okay, compilation is successful. Then we don't have to change anything in vector waveform file. What we need to do is generate a functional simulation netlist. Okay, let us check if vector waveform file is correct or not. In case of Mealy, we have 0, 1, 0, 1, 1, 0, 1, 1, 1, 0. No, it is the same as that was uh, for the Moore machine. Now what we can do is we can simulate it. After simulation, let's check whether it's right. For a clear view, but I should remove the narrations from this. Okay. Now if we look into it and carefully observe, you can see that in the first clock cycle here, our W is 0, Z is 0. Second clock cycle, W1, Z0. Third clock cycle, W0, Z0. Fourth clock cycle, W1, Z0. Fifth clock cycle, W1. It is to be noted that here W is equal to 1, here W is equal to 1. So as soon as two consecutive ones are found, Z is turned to 1. So Mealy machine is working till now. So here W0, Z0, because this is a falling edge. So W0, Z0. Here W1, Z1. Here again W1, second consecutive W1, that will turn Z is equal to 1. Again W1, Z1. Then at last W0, Z0. So we can see that we have the ability to convert a Mealy machine to Moore machine only by the way we define the output. If we define the output as a register and put it inside this else, that is always block, then what happens is we have designed a Mealy machine, Moore machine. And if we keep the output as it is and not a register, and we assign the value of the output, then we have obtained a Mealy machine. So the code for Mealy and Moore machine are the same, only how we define the output actually determines whether the system will act as a Mealy machine or a Moore machine. That's all for this. In the next part, we'll be learning about we'll be implementing pattern generation, pattern recognition using Verilog.